So in our last lectures, we have discussed about aberration, which means simply defect in image, defect in image or blurred image. Alright, so we have gone through the definition of aberration. Then after we have discussed what is chromatic aberration. Chromatic aberration, as we can see here, a diagram. Here is a lens and white light is coming from here. After refraction, it splits into different color: red, green, blue. So there are three focuses here. At this point for blue, this is for blue, say this is F, B focus, and for the green, this point is for green, and for the red one, this is the focus for red color. So this range is nothing but the chromatic aberration. Alright, so we have derived chromatic aberration, derivation for chromatic aberration. So there is another method. So we will see another approach, another method for derivation for chromatic aberration. For chromatic aberration. Alright, as we know, if we have a lens, this is our principal axis, a bunch of beams are coming. Say this is for the red one. Alright, say this is point R, and for the blue one or a violet one, this is violet. Alright, so as we can see, this is our chromatic aberration. This is our chromatic aberration. The difference is called chromatic aberration. But as we know, the focal length, the focal length of thin lens of thin lens is how much? 1 upon f is equals to, we already discussed, effective index minus 1 upon r1 minus r2. This we have already discussed in our last lectures. Now let's say this is equation 1. If suppose, say, if a change of if a change of in diffractive index n by how much? Delta n. Alright, so this delta n causes by what? The change of n is due to the change in the wavelength in the wavelength of the light. All right, so as we change n by delta n, so there must be change in focal length f. So what result in or the results in change in n causes what? F by delta f, f by delta f. All right, so we can say, finally we can say, on differentiating on differentiating equation 1. Equation 1, what was equation 1? Equation 1 was 1 upon f n minus 1, 1 upon r1 minus 1 upon r2. So this was our equation number 1. So after on differentiating this, we get what? This becomes 1 upon f square del of f, sorry, and this becomes delta n only. 1 becomes 0, constant quantity becomes 0, and this is constant for n. This becomes r1 minus 1 upon r2. Alright. So from, say this equation 1, say this equation 2. From equation 1 we can say, from equation 1, n minus 1 must be, n minus 1 must be what? 1 upon f, 1 upon, it must be 1 upon f, 1 upon r1 minus 1 upon r2. Alright. So, or we can say, if we need to calculate, just remove here. If you want this value, which one? This value. So from equation 1, we can find 1 upon r1 minus 1 upon r2 as what? 1 upon f n minus 1. Alright. So just substitute this in equation 2. Subs put the value of 1 upon r1 minus 1 upon r2 in equation 2. So this becomes, the final result becomes 1 upon f square. This is delta of f is equals to what? Change in del n is okay. Whole upon 1 upon r1 minus 1 upon r2 becomes only what? 1 upon f into n minus 1. Alright. As we can see, 1f is cancelled out. So delta f becomes 1 upon delta n upon n minus 1 into f. This f goes to the right hand side. So the value of delta f becomes minus delta n upon n minus 1 of f. Where delta f is, what? A change in focal length. Alright. As we can see, for the chromatic aberration, what was fr minus fv the last lecture? So this is what? Change in focal length. So wherever delta f shows change in focal length. So this result, see, this is equation 3. This result 3 shows what? Equation 3 represents the chromatic aberration, aberration of a thin lens. We have chosen the case of thin lens. Say if NB and NR represents the refractive index, refractive indices for what? NB stands for blue, for the blue, and R for the red one, and red color, respectively. All right. So delta was change in focal length, so I can write it as, but then we can say delta f, what was the equation? Delta f equals to delta n upon n minus 1 negative of f. Alright, so we can say delta change in f. Change in f means for the red and blue one. So this becomes for red, this becomes for blue. So for negative sign, delta n change for nr minus nb, right, upon n minus 1 into focal length. So fr minus fb becomes, just multiply, and this becomes nb minus nr upon n minus 1 into f. So this represents, so this equation represents equation 4. So this is 4. So equation 4 represents the chromatic aberration. The chromatic aberration. Right. So we have seen another method for the derivation of chromatic aberration. Alright. Now our next target is how to remove this chromatic aberration. To remove this, we use two different types of lens just to make the same focus. As we know, till now a white light splits into two different colors, the different focal. This is for blue, this is for red, this is for blue. So we want this to be at midpoint. We can say this is the case for chromatic aberration. So if we want to remove this, so what need to be done? This quantity, what, fr minus fp must be 0. All right. So how this, when this is possible? This is possible only when, so this is a lens system. Any, I'm not making any lens, proper lens. This test is a lens system. After refraction, red and blue must be at the same point. At a same point. If this happens, that means if this happens when a white light goes from some lens system, this is lens system, this perpendicular plane is our lens system, and a red light and our blue light comes at the same focal. So we say this satisfies what, fr fp equals to 0. That means there must be no chromatic aberration. Chromatic aberration is 0. Chromatic aberration is 0. That means our image is free from chromatic aberration. So this property is known as achromatic doublet. Removal of chromatic aberration possible when, this process is known as achromatic doublet. All right. So as we can see here, we had one is uh, lens system is made up of ground glass, and another is made up of flint glass. And white light comes from here. After reflection, all the colors are at the same point. So this is the case of chromatic doublet, where the chromatic aberration is 0. Chromatic aberration is 0. All right. So this is known as achromatic doublet. So how we define achromatic doublet? As we have considered here, what, an optical system, here of two thin lenses, thin lenses of ground glass and flint glass. All right. So we will write here, consider an optical system, an optical system of two thin glasses of two thin lenses made of different different materials placed in contact with each other. So what we have written, and consider an optical system, we have considered an optical system of two thin lenses made up of different material. One material is crown glass, and another is flint glass. Alright, this one and this one is crown glass. Alright, if I may, and placed in contact with each other. These are placed with the separation between them is equals to 0. Alright, this we have assumed. Alright, so we can say one of the lens is made up of what? Crown glass, crown glass, and the other is of flint glass. This we have assumed already. So what we need to calculate, we will find we will find the condition we will find the condition we will find the condition of this lens combination of this lens we will find the condition of this lens combination to have the same focal length, same focal length for the blue and the red color. For the blue and the red color. So we say NV, NY, and NR represents what? The refractive index for different three colors. Represents the refractive indices for the three different colors. Refractive indices for material crown. Alright. What's let NB, NY, and NR represents the refractive indices for the material. Which material? Crown. First material. Crown glass. Alright. Corresponding to what? Corresponding to blue, yellow, and red color. Alright. Same for the, if you want the refractive indexes for what? For flint glass. Similarly we can say N dash P, N dash Y, and N dash R represents the refractive indices refractive for set uh, for the material what? For the material flint glass. Alright, so what we have written, we have one ground material and one is flint material. So for the blue, red and yellow, sorry, for the blue, red and green, we say what, reflecting dash for three different classes for the ground. If we are using dash, so this is for the flint glass. Alright, so, and one more assumption, say if FB and F dash B represents the focal length focal length for the crown and flint glass respectively for blue color of blue color of blue color, and capital FB represents the combined focal length the combined focal length, or you can say equivalent focal length for blue blue color. Alright, the final equation becomes 1 upon FB equals to 1 upon FB plus, this is for ground one and this is for FB dash for flint one. And if the separation between them is 0, so if t is 0, so the third term is 0. So we will use equivalent focal length as 1 upon capital F is equals to 1 upon FB, small fb, this is for crown glass, and F dash B, this is for the flint glass. So this becomes, for this, NB minus 1, 1 upon R1 minus 1 upon R2 plus N dash B minus 1, R1 dash minus 1 upon R2 dash. Alright, where R1 and R2 radius of curvature of crown glass curvature. Alright, R1 dash and R2 dash are for what? Radius of curvature of flint. Alright, so this is the equation. So on solving this, we will get, as we already discussed, 1 upon capital FB becomes NB minus 1 upon N minus 1, 1 upon F. Just substitute the value of what? 1 upon R1 minus 1 upon R2 must be 1 upon F N minus 1. So, so and same here for the dash, this becomes F dash and N dash minus 1 dash plus N dash B minus 1. This the value of 1 upon R dash, this quantity becomes what? N dash minus 1 upon 1 upon F dash. You can write it as, where 1 upon F is equals to N minus 1, 1 upon R1 minus 1 upon R2, and 1 upon F dash becomes N dash minus 1, 1 upon R1 dash minus 1 upon R2 dash. Alright, so for the mean value, we can say N is equals to NB plus NR upon 2, which must be for the yellow color, NY. Alright, Same goes for here n dash material for flint one. This is the mean value, and so this becomes for two different colors is n dash b, this n dash r upon 2. It must be equal to what for yellow color? N dash y for yellow color. So this case for blue one, sorry, this case for blue color. So as we have already chosen for red, blue and yellow color, so we can say for the red, similarly we can say similarly the focal length, the focal length the focal length of the focal length combination for red color, for red color must be just change 1 upon capital R, B will change with R of R is equals to nr minus 1 upon n minus 1, 1 upon f plus n dash r minus 1 upon n dash minus 1 upon 1 upon f dash. So the condition is for the focal length length of the combination to be equal to be equal for what? Blue and red color. This is the case for what? For no chromatic aberration. But I said the the red one, the red color and blue color must be the same point. The red color and blue color must be at the same point. This is possible only when the both the focal length for red color and blue color must be same. So this is what I written here. If this happens, there is no chromatic aberration. So then this must be for the blue one nb minus 1 upon n minus 1 is equals to, sorry, upon 1 upon f. What we are doing, just we are equating, say this is equation 1 and equation 2. Just we are equating equation 1 and 2. So from equation 1 nb upon 1 plus nb dash for flint glass upon n dash minus 1 upon 1 upon f dash must be equals to for the red color nr minus 1 upon n minus 1 1 upon f plus n dash r minus 1 upon n dash minus 1 upon 1 upon f dash. Alright, just take this to the left hand side. So we will have what? What we will have nb minus 1 upon n minus 1 1 upon f minus of this quantity n minus nr minus 1 upon n minus 1 1 upon f plus this quantity n upon n dash b minus 1 n dash minus 1 1 upon f dash minus of what? Minus of n dash r minus 1 upon n dash minus 1 1 upon f dash is equals to 0. What I have done, just I have taken all the elements to the left hand side. Alright, now take the LCM here. I can see n minus 1 or 1 upon f is common in both, so I can take it common. So I can write 1 upon n minus 1 into f common. So what we have, nb minus 1 minus of nr minus plus 1 plus the same here 1 upon n dash minus 1 f dash is common. This becomes n dash b minus 1 minus of n dash r plus 1. So 1 is cancelled out here, here 2, which is equals to 0. So this becomes nb minus nr upon n minus 1 into f plus n dash b minus n dash r upon n dash minus 1 into f dash equals to 0. Alright, I know this quantity. Which quantity? Change in refractive index upon mean value minus 1. This quantity, and this quantity is omega. This is, if I say omega, this is the dispersive power for ground glass, and this for dispersive power for flint glass. So I can write it as, but omega upon f plus omega dash upon f dash must be 0. This is the chromatic definition. So we know omega and O, where omega and omega dash are what? Dispersive power. Alright, dispersive power. For this is for crown one, crown material, and this is for flint. We know omega and omega dash cannot be negative, so these are always positive. So f and f dash must be of opposite sign, sign for, say this is equation for validity of equation 4. Just to satisfy this, I know omega and omega dash cannot be negative. So just to satisfy this equation, f and f dash must be of opposite sign. And in final, a lens combination. This is the conclusion. A lens combination, which satisfies the equation for which equation for this equation. All right, equation 4 is known as an achromatic doublet. All right, so this is what, how we remove chromatic aberration from any lens. All right, so this is achromatic doublet. Thank you.